So this is where we left off, and we were talking about calibration curves, at least the intros to it, and we said standards were very important in the laboratory. And standards should always include a blank and minimum 3. 3 standards are the minimum, but we encourage you to go up to 5 standards. That way, if you mess up on one of them, we can just delete it from the set, and you've got 4 really good standards that you can still use in your calibration curve. We also said that the whole point of these, for the most part, is to get some type of linear curve, some type of line. So when you plot these standards eventually, hopefully they will line up and they will make a linear line or a linear graph for you. Okay, so I'm going to delete this and we're going to clear out the screen and we're going to talk more details about a calibration curve. So 0, 1, 2, 3, 4, and 5. And let's say these are my standards. Okay, so to make a calibration curve, we have to end up with some type of graph. Okay, so we have a graph that's going to be represented down here at the very bottom. This graph, here's the point 0, 0, right? So x increases going that way and the y increases going that way. So this is my x-axis and this is my y-axis. Well, that's eventually where we want to end up. But before we do that, we have to have data points to plot. So we have to have x values and we have to have y values. All right, so that means that over here, I need an x and I need a y. Every single time we make a calibration curve, those are the 2 units that we need. The x number is always going to be concentration. Almost every single time it's going to be concentration. So what types of concentrations can be used in a calibration curve? Anything can be used as long as it's a concentration. So molarity can be used, normality can be used, part per million, part per billion, percentage, any of those concentration units that we have talked about up to this point is fair game. That is a concentration unit. What cannot be used in a calibration curve? What cannot be used are things like grams. That's not a concentration unit. That's an amount. Things like milliliters. That's not a concentration unit. That's an amount. Never plot grams. Never plot milliliter on the x-axis. Not in the field of an analytical chemist. It's concentration based. That is what we're after most of the time. That's what we want to put on the graph most of the time unless we tell you something different. Okay? I'll go ahead and say that in the world of analytical chemistry and an analytical laboratory, part per million and part per billion are going to be the most common, with ppm overriding ppb most of the time. So very often ppm is going to be on the x-axis. Again, normalities and molarities and percentages, they're all really super strong. And our equipment can't handle samples that strong. Our equipment is made to handle very weak samples because we're looking for very small amounts most of the time. So the x unit, the x-axis, has to be concentration. And that's one of the reasons that we write concentration that way, with an x, a bracket around the x. Okay, the y is always going to be the signal, and that is the signal that comes from the instrument. So there's tons of different instruments in the laboratory, which means that there's different ways to represent that signal, and that's why I'm just going to have to give you signal. I can't really say absorbance every time because that's not necessarily the case. So the signal from the equipment that you are using, that is what goes on the y-axis. So let me kind of give you an example here. Let's say that in a lab I've got a blank, and that blank should be a 0 part per million. So I'm going to plot part per million on the y-axis. The first standard that I make, let's say I've made a 10 part per million. My second standard, I've made a 30 part per million. The third standard, let's say I went to 75 part per million. The fourth standard, I've went to 100 part per million. And the fifth standard, I've went to 200 part per million. That just gives you an example. I've made these standards, I've followed my recipes, I've done the proper calculations that I should have, and those are the concentrations that I have ended up making. And these standards are eventually going to be ran on a piece of equipment. Whatever piece of equipment it is, that's going to change and it's going to vary. But I'm going to run these things that I have made. I'm going to run them on a piece of equipment. So let's say that I go and I run these on an atomic absorption instrument. You probably don't know what that is, and that's okay. No one is asking you to know what it is. But I'm going to get a signal. That's what we're the most important part about it. And this signal is going to be in terms of absorbance, ABS. So this is a number that gets presented from the instrument. And I just write those down, right? Who cares where the numbers are coming from at this point? I don't care if you know what atomic absorption is. I don't even care if you know what it's supposed to be measuring. Only thing that we need to do, that we need to know to make a calibration curve is to know the signal. I need this signal from the machine. Who cares what the machine is? Who cares what's happening with the machine? I just need the number, the report, and then I can do whatever I need to do with it. So I'm going to quickly write down some absorbance values based on these standards that I've made in the lab. So here are the concentrations. So when I ran the blank, I got a 0.02 absorbance. I ran my 10 part per million and got a 0.51. I ran a 30 part per million, got a 1.53. I ran my 75 and got a 3.96. I ran the 100 and got a 6.18. I ran the 200 and got 11.46. So these are just the raw numbers that came from the instrument, right? And again, those absorbances don't mean anything to me. If I was just given the absorbance and that was it, I have no clue how that absorbance relates to anything. The machine doesn't know either. The machine is stupid. It doesn't know what you want to do. It doesn't know what kind of sample that you have made. It doesn't know what type of sample you've presented it. The only thing it does is do one job, and that's to analyze how the sample is behaving in whatever kind of setup that it's giving it. So it just gives you numbers. That's all that it does. It's not going to do anything else for you. So it's my job to do a calibration curve. And the purpose of the calibration curve is to figure out how the concentration relates to the signal. That's the whole job. That's the whole purpose of this calibration curve. That way, when I run a sample, and my sample, let's say, gives me an absorbance of 0.713. Well, I can compare that now to something that I've made in the lab. And if my absorbance is 0.713, then I know that my absorbance is going to have to be in here somewhere. It's going to be in between the 10 and the 30 part per million, because that's where my absorbance falls, in between the 10 and the 30 part per million absorbance. That's the purpose of the calibration curve. That's why we do them. That's why we make them. And that is the power of you, not a piece of equipment. So, I've made a set of standards. They went up in concentration. And you, before you do anything at all, you should look at your absorbance. Did those go up as well? Most of the time they go hand in hand. So if they did, you can kind of step away from this in the beginning and say, well, they don't look too bad, right? My absorbances went up as my concentrations went up, and that's what should happen. So I can automatically look at this table and say, well, I probably do have pretty good data. Another thing that I can use to judge is this 10 to 30. right? The 10 gave me a 0.51, and if this is really linear, if it's supposed to be a linear relationship, well, 10 times 3 is 30. 0.51 times 3 is about 1.5. So I can use this as a quick judge to see if I'm even in the ballpark, right? Well, if I look at this 10, 0.51, and 100, well, that's 10 times the amount. What's 10 times 0.51? Well, that should be like 51, not 66.1, right? So because of that, I'm going to maybe realize that one of these standards is kind of out of whack. And we'll see that when we eventually begin to plot them using Excel. So what I want to see is that when I plot these numbers, right, my concentration goes up unit-wise, part per million. My absorbance values will go up accordingly. And what we hope to see is a line that goes through those points. And if it doesn't go through every point, no big deal. We deal with that. Nothing's ever going to be perfect. And we'll talk about how to make them better. But overall, this is kind of the concept of the calibration curve and how it's going to get structured and what its purpose is, right? So you make a set of standards in the laboratory. You know what those concentrations should be. Those get ran on a machine. You get a signal. And this allows you to relate a signal to the concentrations that you're using. That way, when you run samples that have an unknown concentration to them, you'll get a signal that's associated with the sample. And you can quickly go to the table or your calibration curve and figure out where that number lies to maybe estimate and eventually perfectly solve for that concentration of the sample. One more thing I want to talk about before I stop the video, and that's the blank. Notice that this blank did not read as 0 absorbance. This blank ran as 0.02. Blanks, it's okay if they have a very small signal. That's normal. Okay? The instrument, there's air associated with it. There could be air associated with the solvent, the blank that you've used. Maybe it contributes a little bit to the signal. Not much, but maybe a little bit. Whatever the case is, that's the purpose of running the blank. The blank should hit close to 0, though. If the blank doesn't hit close to 0, then that means something in it is really contributing to the absorbance, and we don't want that interference to take place. So when we make these calibration curves in the laboratory, we kind of want to see it hit close to the 0 mark. It could be a little bit above, it could be a little bit below, and that's okay, but it should be close to 0. If we ran a blank and this blank ran an absorbance of like way high in the very beginning, then that's probably not the proper solvent to use to make those samples with. Maybe we need to choose something different. So in this case, if I used methanol, maybe we need to not use methanol, and maybe we need to pick another solvent that everything is soluble in that doesn't give me a very high absorbance read on the instrument itself. So blanks should be included in the cal curve. Blanks should be analyzed with your standards. It's okay if blanks have a very small signal. That's fine. No big deal. But blanks should not contribute largely to the signal of your sample, meaning those numbers should not be very high at all. So we plot them, we include them, we run them, but we want them super tiny when they show up. All right? So in the next video, we're going to take this data and we're going to actually make a calibration curve with it using Excel.